Hi, this is Xiang Cheng from Peking University in China. Thank you for opening my talk. I'd like to talk about why are gravitational wave sources so massive and its implications for LISA. We know LIGO Virgo have detected a lot of binary black hole mergers, as is shown by these blue dots. The interesting thing about them is that they are all very massive. If you compare the gravitational wave black hole masses to the black holes detected by electromagnetic waves, such as those black holes in X-ray binaries, you will immediately see that gravitational wave black holes are several times more massive than the black holes in X-ray binaries. The most massive gravitational wave black hole has already a mass of 60-90 solar masses even before the merger. So why is that? Why are gravitational wave black holes so massive? There are many explanations these days. One of the mainstream explanations is that these black holes form in binary stars, both of which are very massive because of their low metallicity. These stars in low metallicity regions will form very massive black holes during their later evolution. And the masses can be as much as 30-40 solar masses. So the key point is that you really need a low metallicity to form these massive black holes in binary stars. The other model is that black holes might form small, but they form in dense regions like star clusters, and the later repeated dynamical interaction would capture another black hole and make them merge. Through these successive mergers, small black holes can also grow to very large masses. But when my collaborators and I looked at the problem, we asked ourselves another question, which led us down to a very different path. So the question we asked ourselves were, how are masses measured? In the end, what you detect is not the mass itself, it's a wave. So a wave has three properties, three observables: amplitude, frequency, and a time derivative of a frequency, or frequency dot. These observables are related to physical parameters such as the masses and the separations of the black holes. Only through a theoretical model can you infer from these observables the real physical parameters. Since astrophysical binary black holes are mostly on circular orbits before they merge, so you can use the circular orbit approximation plus some Keplerian approximation, and then you can combine your frequency and the frequency dot in this way to get rid of the dependence on the semi-major axis, and then get a mass scale as is shown here by the chirp mass. So this is called chirp mass, and it is a mixture of the masses of the two black holes. You have a third of observables that you have not used yet, which is the amplitude of the gravitational wave. So you can use it to further infer the distance. This is because the further away the source is, the smaller the amplitude is. Since we use amplitude to detect the distance, it is like we use sound to infer the distance of a sound source. That's why gravitational wave sources are also called standard sirens. We use loudness to infer the distances of gravitational wave sources. But the universe is more sophisticated than that simple model. We know that the universe is expanding. So what the expansion does to a wave signal is that it stretches the wave signal. So in the end, the frequency you detect is no longer the real frequency, it's redshifted. The frequency dot is redshifted even more because of time dilation effect. If you wish to combine the new observables to get a chirp mass, then this observed chirp mass or apparent chirp mass is not a real chirp mass, it's bigger than the chirp mass by the redshift factor. So this is called the mass and redshift degeneracy, because unless you independently measure the redshift, otherwise you do not know the mass. You always overestimate the mass because of the redshift effect. Don't forget that you also overestimate kind of the distance, but in standard cosmology, the larger distance with the redshift in it happens to be the luminosity distance. So we recover the classical notion that using gravitational waves, you can detect the red luminosity distance. This is of course very important for cosmology because when redshift is large, you have to consider the effect of redshift on the mass and the distance measurement. But astronomers know three types of redshift. Besides cosmological redshift, there are also Doppler redshift. If a source is moving very fast away from you, you will see the source Doppler redshifted. There's a gravitational redshift. If the source resides in a very deep potential, the wave signal will also be gravitational redshifted. So why so far LIGO, Virgo haven't considered the later two redshifts? Of course, there are reasons. Like I mentioned before, in the conventional formation channel, binary black hole sources form in the galactic disks, in the field of a galaxy, in the bulge, or in globular clusters. In all these environments, the velocity, the center of mass velocity of gravitational wave sources are not so big, so people think the Doppler shift can be neglected. The potential is not very deep either, so people think gravitational redshift can also be neglected. However, a lot of works in the past few years suggest that the conventional view of binary black hole formation, at least, is not complete. People found that in the centers of galaxies, especially close to supermassive black holes, there is an enhancement of binary black hole formation and merger. You can see a review in this work in 2019. One of the model along this line that you form more binary black holes in supermassive black holes is that in AGNs, the accretion disks can form and capture a lot of stellar mass black hole in it. It turns out to be a relatively old idea. So from the 1990s, people have already realized that accretion disks are very good at capturing and forming stellar mass black holes in it. The black holes will migrate in the accretion disk due to interaction with the surrounding gas, capture each other also due to the interaction with the surrounding gas, and they merge because these black hole binaries are embedded in gaseous environment, so hydrodynamic friction can lead to their merger. The merge rate is a bit difficult to estimate because of a lot of uncertainties about the properties of the accretion disk and also about star formation in the disk, as well as the distribution of stellar mass around the supermassive black holes. But the rate can be very high as 10,000 per cubic gigapascal per year, according to some calculations. If these black hole binaries form very close to a supermassive black hole, then they're moving very fast. Doppler shift cannot be neglected. Gravitational redshift can also be important because now the potential is very deep. You can estimate this effect by putting in Doppler and the gravitational redshift into your equation for measuring gravitational wave source mass, and you will see that the mass is even more boosted because of these two effects. How large this later Doppler and gravitational redshift is depends on how close your source is. So if you imagine a binary black hole source like this red point is circling around a supermassive black hole, in the simple case, the central supermassive black hole is not spinning. You can calculate the total redshift factor. You notice that the ISCO innermost circular, stable circular orbit is at a 3 structural radius. The velocity here is 0.4c, very large. So the maximum redshift due to Doppler and a gravitational wave, gravitational redshift is almost 2. If the central supermassive start to be spinning, then the ISCO is even closer. So according to some calculations by my student, the redshift can be as large as a factor of 3 or even larger if you put it extremely close to the ISCO. Don't forget that you also overestimate the distance because there's also a redshift factor here. The implication is that a small and a relatively close-by source due to the Doppler and the gravitational redshift will appear more massive and at a much larger distance. If you have an independent way of measuring the distance of the gravitational wave source, see using electromagnetic waves, you will see that the gravitational wave distance is larger than the electromagnetic wave by a Doppler and a gravitational redshift factor. Interestingly, the most massive LIGO Virgo source GW190521 has an AGN counterpart, or candidate AGN counterpart, and if you look at the distance of the AGN and the distance from the gravitational wave source, they are not completely consistent. Okay, for other people, this immediately tells them that the two cannot be associated, but in our model, they could be associated if the gravitational wave source is heavily redshifted. In summary, we think it is an interesting phenomenon, and we think it will have important implications for the detectability of massive binary black holes by LISA.